So today, the second talk will cover that matrix inversions, and this is very fundamental to start with because some of the talk already started, discussions already started about the data model relationships and how we can infer some amount of the informations from the data itself. As a geophysicist, actually we start with that field work at any field site, and we deploy the equipments, and then we collect the data according to some of the survey pattern. So if you are a geophysicist, have the amount of the knowledge about the equipments and the theory, for them it will be very easy to understand all the process. And then somehow we collect the data according to some survey plans, and we have the data, and finally from the data we need to process it through some processing schedules, and then we interpret it, and basically we deal with that from the observations, and we need to provide a set of models or model parameters which is related to the properties, basically from the Earth's properties, Earth's physical properties. So Earth consists of different layers. Each layer consists of different rock types. They have been deposited in a different time, different sequence. Their physical properties is a function of the time, the depth where it is deposited, and lot of this pressure, temperature, all these things are actually coming into the picture, their physical changes. And from these observations, it is a very difficult job to inference about the physical properties at a point of time, because it actually contains a lot of steps in between that. And that is why we call these inverse problems. From the observation to the inference about the model or the model parameter is a very difficult job. And then we will discuss about the complexity at different stages where we actually face it. Looking at the mathematics is a one aspect. The second thing is that we have to use also our physical knowledge. If you are a physicist having a background of the sound physics, you will apply the physical theory to understand the forward theory. Then if you are a mathematics background, we know that what are the different mathematical techniques, calculus, algebra, then integral equations, all these things, which will be applied on the data to infer about that, what are the inference about the models of the model parameters. So in this way, actually, we will deal with invariably the two parallels of the philosophy. One is that data to models, and then model to data. That is how we can say that which actually comes first, chicken or egg. From where we will start it, which comes first. You have the models parameters, then also we need to know that, or we want to predict the data, then also we require the sound physics or the physical theory which relates from the model parameters to the data. Now you have the data. Now what will do that? From the data, what will do that? So if you want to again make any inference from the data to the models, this process is an inverse process, or the inverse modeling we call it is formally, and that requires that mathematical theory is required, and that is also not sufficient, because this data, no data is noise free. In the real world, if you see which one is the ideal, nobody can say which one is the perfect, which is the ideal thing. Ideal thing never be existed. And invariably those who are field specialists, if you visit some amount of the field, geological fields, geophysical field or geochemical field, hydrological field, mining, surveying, all are invariably lead with that we are associated with a different type of complexity from the data. When you are collecting the data, whether your instrument is providing the correct data or no, whether the instrumentation which is there inside, that is also correct or no. And then when you are collecting the data, that also associated with some amount of the error which is called the human error. Let us say I am operating one instrument. So I have my limitation, the precision. So I can visualize some records which is based on optics. That also may associate with some amount of the noise. And there are a lot of or many sources of the noise are there, which are actually we cannot avoid it from the point of the view. So ultimately what it is left with us that we have to deal with this, the noisy world. And nowadays, this AI, machine learnings, they are actually coming into the picture in a big way because it has the adaptive natures that we will discuss, that how it can indifferent to the noise presence in the observations. Once things is that some things we cannot recover it. We call it, we can treat it. Treat it means we cannot avoid that effect of this one. That is why we need to develop some amount of the systems, the algorithms, or the say of the systems or algorithms or combination of that can handle both the things. So with this background, I can start with that some of the questions we put in the framework where we ask and then we again ask, then this asking and searching for the answers will give you enhance our knowledge enhancement. So there are two ways we can handle it, the data model relationship. One is that selection based, another is the deduction based. So usually we'll follow that some of the philosophy where some of the well established literature is there. So this is one of the books, Menke, which is a very common and the very established book in the academics, where you can get the data model relationship in the matrix format, how the functions are related with the data, with the model parameters in a very simple way. So anybody can start that the inverse theory. I would recommend a book called the Menke, which is on the geophysical data analysis. There is a versions of the MATLAB functions so available. These are the books which has been written for the seismology, for the internal structures of this earth, and some of the books which is written for the geophysics or the applied geophysics. So everywhere in the book you will get one chapter which is fixed. That is called the inversion or the inversion methods. Because all the data as a geophysicist we actually handle it, they are actually collected on the earth, and we are handicapped with that. We want to know that physical properties which is varying inside the earth, where we cannot go, we cannot reach, we cannot deploy the equipment at any of the depth. So that is why the exploration geophysicists or the applied geophysicist people, they invariably call it as inverse scientist. Because without that, they cannot infer the amount of the information which is actually seeking for. So some of the very review literatures which is available in the net, some of the books which I recommend, that Monte Carlo, where Professor Sen will be talking about that stochastic inversions, where this type of review geophysics papers are elaborate and they are very exhaustive for providing all sort of details. So usually in my teachings, I refer some of the very standard books. One is the Menke, where I said. Second is the Global Optimizations book written by Professor Minal Kesen, who was with us during this all these GAN programs. There's a book by Gavins, which is actually written on the time series and inverse theory. That is also another good book. And usually some of the concept we have taken from the reference book second, which is that Scales and Smith, Scales et al., with the help of this Strittle 2001, which is on Introductory Geophysical Inverse Theory. That is also a very short note, which is publicly available on the internet, very good to start with. And this Tarantula book, which is dedicated for the inverse theory using the probability theory. Probability or the probabilistic estimations, we start with this book called the Albert Tarantula. So we, in the matrix inversions, before going to that, we will talk about that what is overdetermined problems, what is event-determined problems, underdetermined problems, because this type of information is required to identify that the types of the problems as well as the what type of solutions we want to employ it for deducing the model parameters. Because when we will deal with these inverse problems, we have to answer so many questions at a time. One is that what type of optimization technique we should employ. Second is that we are dealing with the data, how the data is accurate, whether this data is noise free or no. So if you see that okay, noise invariably it is there, we cannot handle it. Then the second things is that we have to develop or some techniques, or we have to know about that what type of noise is there. That means we should know about that the types of the noise which is present in the data, or the classification of the noise. And then once it is there, then we have to answer that what type of techniques we have that can handle that noise. How we can handle this noise? Either you can remove the or delete the noise, remove the noise from the signal. Otherwise, if you are unable to do that, we are not able to do this remove of the noise from the signal completely, then we have to develop some technique which is robust. That means if the noise is there also, then also your optimizations or the algorithms can handle the most of your answers we are looking for. And there are some decomposition technique we will go through, and then the associated the theory related to vector space, Hilbert space, and the norms. Norms is the last one, which is the very important to understand that which type of norms we should use it. So some of you have the questions in the first half. That is very good. That what type of noise? That is also one part in your inverse practices. That what type of norms actually we should select it to handle that the problems or getting the solutions in your reasonable accuracy. Usually when I talk about that, one statement I like and I want to share with all the participants here, that using observations to infer the values of some parameters corresponding to solving an inverse problem. Right? And practitioners like us usually seek the best solution by using this inverse theory. How it is? It should be implied by the data, but the observation should only be used to falsify the possible solutions, not to deduce any particular solution. Okay, what does it mean? That means that there are two ways we can handle this inverse problem. One is that the selections. Selections means we have the solutions, we want to select the solution, particular solution. Another approach that we don't want to select this particular solution, but we want to reject the solution. So this theory is actually very effective because, say, jumping a solutions that may not give the enough confidence that whether this particular solution is correct or no. Rather, we can use a alternative approach, reject a solutions what you get it, then again reject it, then again reject it, and so on. And finally, what is the solution? Last solution left with us, that will be the possible solution to answer your inverse theory. So this statement is used by the Albert Tarantora, one of his paper published in Nature Physics. So you have these relations with these data models, relations that we start with any of these. Because if we move from the model to the observations, then your forward problems which guides you. The reverse is your observation to the data that gives you the inverse problem. And if we want to know the correctly to reproduce these observations, we must have to know that physics of the forward problem. Right. But when we are moving from observation to the models, we should be very confident about that what type of mathematical framework we are deploying or techniques to get it. But this is a process which is not the final answers, because you see most of the cases in our geophysics, this data model relationship is complex. In sometimes it is most of the cases it is a nonlinear, as some of the examples we have already, you have seen in the previous lectures, that how you are approaching or handling this, approaching this inverse problem to solve will give you that whether the problem is linear or the nonlinear. There are types of the noise, whether this linearity, the data model relationship is only linear, highly nonlinear, or quasi-linear. That gives you again the degree of confidence that what type of algorithm we should use it. And most of the cases you see that, particularly we'll discuss about the resistivity inverse problems, they are actually a very highly nonlinear problems. So we have to use some of the linearization method, or we have to use the purely nonlinear approach by data-driven modelings or neural network-based optimizations method to get these model parameters. Model parameters, they are in a, say, true resistivity of the earth, true resistivity of the each layer of your earth from the observations, say apparent resistivity in electrical case. So there we want to solve a very highly nonlinear problem. That can be based on your gradient based or say Newton's based, or it is a combination of your standard methods with the data driven. So nowadays this data driven is taking into the front seat because it can handles the nonlinearity particularly in the data model relationship, and it is a iterative way can handle the amount of the noise which is present in the data. So this, the again problem is that as we have that statistical characteristics of the noise we do not able to know, or we are not able to know a priori before starting the inverse problem. Noise is there, but what type of noise is? It is a purely Gaussian, or it is a correlated Gaussians, or it is a stochastic, or it is a chaotic or logistics map, or it is some other form of noise whose statistical distribution is not known. So most of the literature will find it that our data follows this normal Gaussian. It has a bell-shaped curve, and the mean variance will give you the distributions. But in real world, many of your data is our correlated one. Correlated means data in the model has some relations, correlation structures. And that type of correlations, no filtering theory can allow you completely remove that type of noise from the data. So they are deceptive in nature. Deceptive means whether they are present in the data, we call it as a signal, or no, it is very difficult to see and visualize or identify this noise in the observations. So again, separating this noise from the data itself is an inverse problem, or it's a non-trivial. Non-trivial means it is not the linear process, which we can remove that one. So that is why my third point is that noise can be random, noise can be stochastic.
Normally the noise by stacking the measurements also, we will take that 5% difference. If there is an acceptable criteria, then we will be removing that. Then how can we identify the exact how much noise is there?
So it is a good question that in our seismic also it is there. Through the stackings actually we enhance the in-phase components of your records, and but these are all applicable or good for the noise which is Gaussian type or the random noise, because this will give you that random noise is there, so they do not have any trend. So if you stack it, then in phase and out phase will be cancelled out. Obviously, it will give you the signal enhancement amount. But the thing is that we are talking about that all the noise are not the random or the purely Gaussian. Some amount of the noise are actually the correlated Gaussian. Correlated Gaussians, or we can call also a correlated noise. So we will discuss in detail about the types of the noise here. So for them, if it is a correlated one, so stacking will not help you, because that is already has some relations with the data. If you stack it, that part also will be actually mixed with the signal and it will enhance it. So what is the stacking concept? It is there, mostly it is applicable for the Gaussian on the random noise on the data. Whether you go for the seismic or any other electrical records we dog in the field work. Later we will see that why we are doing. Usually this Gaussian noise can be determine if you do some power spectral analysis of your data. So you do that data or the time series data in the Fourier transforms, calculate the Fourier power spectrums and plot this Fourier power spectrum with this wavelength. And then you will see this, the type of the spectrum. If it is a purely Gaussian, it will be a flat spectrum. That means that type of all sort of frequencies are present in that. That is why it will be a flat of the power spectrum, a flat spectrum. So from that you can identify it. But if it is a not purely Gaussians, then it will be not the purely like a flat spectrum. So some amount of the power will be there, which will actually occur in between data part as well as the noise part, and that is very mischievous. Whether you can treat it is a signal of the data or whether it is a noise, that is actually non-trivial job. Because we have to deploy some filtering technique. We have to define the cutoff filter, either it is a low pass, high pass filter, and how we will select this cutoff frequency. So if you put this cutoff frequency towards a data site, then you are losing the data. If you put this cutoff frequency towards a noise site, then noise will be into your data. So it is a non-trivial task.
Only if you go deeper, the noise will be from shallow to deeper, the noise will be increasing with depth, right? So at each every point you have to filter the noise, right? So different filters you have to use at different depth, right?
So that is there. That is another concept, because that you called about the noise distribution is it our depth dependent noise. Usually you see this. In fact, the potential field data, if you have the anomaly and if you distribute it in the different depth through your say upward and the downward continuations of your gravity field, let us say, there you will see the most of the data which are noise free looks are deeper structure. And you will get this very smooth variation of your true picture of your Earth property. But you see this, there will be a lot of features which is actually, it is a geological or not geological. That will be difficult when you move towards a surface. That means if you actually plot these things in your power spectrum, there also you can see this, the dominance of this noise from the different wavelength or frequency, because wavelength and frequency again related to the depth of the interest. Whether you are applying the low pass filter or the high pass filter or intermediate filter, that will define. If it is a low pass, then the long wavelength will be passed, and so the gross structures will be enhanced. If it is a high pass, then the high frequencies things will be there and it will be actually create a problem. So this way we see this, the data models can be, noise can be also a part which is mixed with the data in an additive way and the multiplicative way. There is again two ways this noise can be mathematically added to your data part. So this model says that D is your data, G is your kernel matrix, M is your model parameters of the models, and plus N we call it is error or the say random noise. So this type of models is called the additive models. Here your noise is related to the data in terms of in added model. It is added. And G is your, what is G? G is your kernel matrix or operator. So we are applying on the G which actually relates between the data and the model parameters. Now what type of information G contains? G in this form it shows that it is a linear form because it is not a function of the model parameters. So in the linear inverse problem can be stated in this way, and it is a noise part which is added to your data vectors which will give you the observations, which is called the real model. And if you assume that there is no noise is there, this N part will be removed. So D can be predicted using the help of the G and the M. N is the noise there. You can call it is a noise, or otherwise you can also say it is that D minus GM. That means if your theory is very perfect and your data is not there is a no noise is there in the data, then with the help of the G and the assume physics, say M, we can exactly produce the D. But the problem will start that we do not know the statistical characteristic of the N, type of the noise presence in the data, and the G, we assume that is a linear inverse problem, so G is a linear one. But G also contains the physics of the problem, the informations. And G also takes the information about that, what type of survey design you are deploying. So the survey, the type of the survey, the design of the survey, that type of information is also incorporated in the G matrix. That also a part of your physics, we can call it a. So there we will see that this noise can be added, can be generated, and understand the two methods. One is that autoregressive one. Here your xt is your time series, and xt minus is your previous time series. A is your constant that relate to your maximum likelihood constant, and again this is a random component which gives you that the noise, random noise we can call it. Through that also you can generate that autoregressive models, that is a stochastic noise, you can generate it and simulate it, what type of noise levels present in the data. That is the way we can understand the characteristics of the noise. And whether your noise can be a chaotic, then the second equation will follow, the xt plus 1 equal to some constant, we can call it some controlling parameters, with the xt 1 minus xt. This equation is very simple, but these equations is a logistic models, and it actually provides the complicated dynamics it can explain with this simple model. And you will see this by changing the constant here, say b, you will see the different type of time series or the signal, and that will vary you the complexity from lower to the highest order. So b varies from say 1 to 4, and 4 gives you the maximum, and we call it is a complete chaos. And that way theoretically we can generate the types of the noise. And you see in the 3D plot there all these natures are there, how they have been distributed it. And this is a techniques we will discuss in details, that from the time series you can generate this power spectrum and the autocorrelation functions of your time series, and by this we can also able to find out that if any signals is there, what type of noise is there, what is the noise is corresponding to the chaos, whether this noise is stochastic, whether this noise is random. So these systems, it is automated system which can discriminate the types of the noise present in your signal. So this left side is showing that this is your original data corresponding to the different model, basic model. So first one is the stochastic one, autoregressive one, second is the logistic maps, third one is the random. And they are these spectral characteristics, and then by applying this ML theory, we are able to find out that, say, given a time series, say first one, then these systems will discriminate the presence and the dominance of the different type of noise in the series. And how it will start from this? So left side is your basic data, and this is your extracted informations, and using this AI ML, we can able to predict that particular series and what type of noise is dominated in the whole time series. And this type of theory can be applied to any sort of data, because we are applying, say, seismic stress in resistivity signals. In fact, in electrical and MT, we have dealing with the time series, and there are a lot of noise components are there. That noise can be your electrical noise, power line noise, that noise can be your human noise, that noise can be your vibrations, that noise can be a coherent one, noise can be incoherent one. A lot of things are there depending upon their phase and the other characteristics. And as I say, you summarize that whether this noise can be of different types. Either it is a correlated one, we call it is a colored one, and it is uncorrelated one, or the purely Gaussian. So this type of classification is based on your statistics. And in under this correlation, colored noise, there can be a red noise, there can be a blue noise, there can be a pink noise. These are all the types of the noise which is actually present or the established in the literatures. And if you go for the classification based on the phase relation, whether your noise has some constant phase relationship, then we can classify then either it is a coherent or the incoherent one. If the constant phase relationship is there, then we call it a coherent one. If it is not there, then incoherency is there, and which is actually required for your different identification of the noise and their removal process. So before going to this techniques about that underdetermined, overdetermined, exact determined theory, let us go through a free route through which we can have that most of your elementary algebra is required for your inverse. When we will actually give you that matrix-based inversions in, say, let us say in tutorials, in other classes, they are invariably we put that data in a matrix forms or the vector forms, model is another vector forms, and the data model relationship constitute the G that constitutes a matrix. And we need to find out that matrix, say G or G inverse. And for employing the G inverse, we also need to know that some of the basic properties of the operation which is required. So you have that matrix consists of elements, it has a rows, it has a columns. We need to find out the matrix transpose. So A transpose, if you change your this row and the columns, it will provide the A transpose. There are some properties. What is the symmetric matrix? What is the skew symmetric matrix? So if the A transpose equal to minus A, then it is a skew symmetric matrix. Okay, so matrix can be partition it by using this formula. So A, it is a combination of A and the A transpose. And this type of operations is required to matrix algebra. So there is a Hermitian matrix which says that a Hermitian is a square matrix that equal to the transpose of the conjugate matrix. There is an orthogonal matrix where A transpose is equal to A inverse, and from that you can able to find that A inverse, if it is a orthogonal. There is a diagonal matrix where diagonal elements are there. There are square matrices, you know that if it is a square matrix, then it is easy to find out that A inverse. And but in the inverse theory, many of the cases this G cannot be a square one, because the data and the model, they may not be in the same dimensions, the same numbers. That gives you that G is a non-square. So evaluating the G inverse, if it is a square matrix, there is a straightforward way to do that. But in most of the cases, it is not. That is why we require some special or the decomposition based technique like singular value decompositions or orthogonal transformations to find out that the inverse of the G. Because this is one of the technique which is or the basic things we require to find out that the model parameters from given the data sets. And invariably, yes.
Given much to matrix and not any other
Pardon?
Why the preference is given much to matrix and not to any other alternative?
So usually we solve these two type of inverse problem. One is that continuous inversion. Another is the discrete inversion. Continuous inversions means the theory which we require that continuous distributions of the physical properties inside the earth. That means our record should be continuous in time and the space. And that contains a huge amount of the information. So in order to deduce some theory, that from the continuous data to infer that continuous distribution of the model properties, that is more challenging. That is why we discretize our systems, that because of the two reasons. One is that it requires less amount of the informations to describe that the gross distribution of the earth, and for the discrete mathematics of the discrete algebra, there is a lot of scope to handle this, to deduce this model parameter from the observation. And in fact, in practically, we cannot measure continuous distributions of your properties by any of your instrument. Because as a geophysicist, we collect a data set at a particular point on the Earth's surface at the geospatial coordinate. Then we move just to new locations, again deploy it according to some pattern. So obviously the data mostly we collect in a discrete form, not in every point of the Earth's surface, because Earth's surface is huge and it is physically not possible to record every point on the Earth's surface on the equipment. And the discrete things, it is a very easy to project in a matrix format. And that is why it is essential, because invariably we are actually handling with the discrete inverse theory. We are not focusing on the continuous inverse theory because of this type of limitation. Clear? So when we talk about that your G is actually non-square, there we need to deduce it. So singular value decompositions is one of the effective technique to deduce that how your matrix can be decomposed by the combinations of the three matrices. They are of orthogonal and orthonormal. And here we have to find out that the characteristic equations of the eigenvalues and the eigenvectors to find out the root and the solutions, because this SBT will be used to deduce that damped least square base inversions we will discuss about the resistivity inverse problem. And there we will see that this matrix deterministic equations can be solved and this lambda can be evaluated, and with this help of this lambda we can find out the eigenvalues and the eigenvectors of your given matrix. So now the two things is very important, which is that what type of information is actually heavily available in your inverse problem. When we formulate the inverse problems or the data model relationship, we also make sure that what type of information is available with your hand. If the amount of the information is more than the number of the informations we want to estimate in your inverse problem, then we call it is a overdetermined problems. Usually it is a simple to find, because we have the more number of the data of the control and less number of the parameters in your characteristic equations to find out. But again they will be having a problem, because your underlying fitting or regressions cannot explain each of the data point in your. So it is actually least squares based average methods which actually compromise that the most of the data which is handled in your problems. Right. Now coming to that, another type is the underdetermined problem, where you have a less informations in your hand, but you need to know about the more number of the model parameters in your inverse problem. So that means it is a more challenging than the overdetermined problem. So we actually, or strictly speaking, the underdetermined inverse problems does not have any straightforward solution. So overdetermined problems can be solved using these least squares based methods, the least squares methods, where your misfit functions is defined as a dp is the predicted data theoretically, d is your observation data, and this part is actually your error. So E transpose E, so dp minus d transpose dp minus d, that gives you the loss functions or the error functions. which is defined based on the L2 norm. Why it is L2 norm? So we'll talk about these norms later on. But for being, you see this is error and the error transpose. So it is a E square. So there is a part that it is a observed minus predicted and to the power square and to the power square root of the square. That gives you your L2 norms. And this gives you that model parameter estimated. It is a G transpose G whole to the power minus 1. So G transpose G has to be estimated in your given matrix inversion problems to find out that model parameters.
Can you define the conditions when you should use what I want? Like, there's a norm, there's a norm. I mean, it's so that when you are trying to break the different norms, how will this means to be applicable? But still, can you say that in this kind of situation, like in this kind of problem, there is no norm.
So usually, as mathematically, we define that law norms from L1 to L infinity. L1, L2, L3, L4, L5, like L up to infinity. There is a norm which is theoretically can be defined. But most of our geophysical problems will deal with the two types of using norms. Either it is L1 or the L2. Because that L1 and the L2 norms actually defined based on the two school of philosophy. These L1 norms mathematically defined, it is the absolute difference between your observed data minus predicted data. Okay, this is the absolute difference. This is the absolute difference means this type of minimization is based on the absolute difference between the two reference plane. Where this L2 norms, it is a square term is there. So mathematically also you see this, that suppose you have the data, you assume that it is a noise free, no noise is there, right? So in that case, I would suggest this L1 will be more stable solutions. Because these L1 norms, these absolute based norms, actually it is a more stable if the noise level is less. Even if it is a noise level is high also, this it actually indifferent to that one. Whereas if the noise level is high, say suppose the outliers is there, then this L2 norms will actually amplify the amount of the one noise will amplify the whole
Number of these norms. Because of the square terms. So suppose this one noise or the one outlier presence in the data, that will give the whole mean of the statistics. And it will be amplified if you use this L2 norm. That is why if your data having associated with the outliers.
right. So in that case, it is recommended to use this L1 because L1 is a lower rank. It is only based on the absolute difference. So if your amount of the noise is very high also, this will not give you that much of perturbations in your optimizations. But if your outlier is there in your data, then what will happen? Then if you apply these L2 norms, then because of the mathematics, actually it will amplify it. So it will be more unstable if the outliers is present in the data. So there are two cases are there, very clear. If your data is having an outlier, then it is recommended to use this L1 norm. If your data is no outlier is there, then L2 norm is preferred. But this preference of your L2 norms in environment, and again it is depends upon the thought call that L1 norm is coming from the LPP, the linear programming. It is actually difficult to code it. While this L2 norms, it is coming from the linear algebra. So it is a very easy to express, very to actually use it. So the philosophy is that popularity of the L2 norms is much more than the L1 norm. In all literature you will find. If we find any inversion papers or any literatures which is dealing with this L1 and the L2 norms, here you will see 90% users are using the L2 norm. This because of this L2 norms is not because of the things that, because it is very easy to define it and it is coming from your algebraic expressions. Where this L1 norm is absolute based methods, and that is actually more robust, we can say, if the outliers is present there. So if I ask that if the outliers is present in the data, which one is the robust, then L1 is the robust. If the outliers is present, then L1 should be used. If the outliers is not present, then I would recommend this L2 will be more effective to use that one.
Any number of norms is possible. Have you ever used any other norm except L1 and
It is possible to use it, but the problem is that most of the things which is actually handled in that, either you can use it L1 on the L2 or combination of the L1 and L2 is also there. There is a mixed norm. Mixed norm means that the norm has been defined by combination of the L1 and the L2. But the use of your L3 and higher order norms are actually very rare because of the mathematical problems is there to define and execute it. And they are not very supportive in terms of your, say, noise part, what we are actually talking about that. Most of our noise is actually either Gaussians, and some of the noise are actually complex, which is actually non-Gaussian or the correlated, we can say it. So in that cases, neither L1 nor L2 or any type of noise can handle it. But your data distribution, if it is most of the cases it is Gaussians, we can recommend that we should use this L2 norm because of the Gaussianity. Because Gaussian is the concept which is the average one, and most of the standard theory is actually based on. Either you are mean, mode, variance, all the things we calculated or estimated in your estimations, they are based on the Gaussian. But in non-Gaussians, there is not exact theory is there. The problem is different. Problem is that non-Gaussian theory, there is no analytical things which is actually established. And if it is a problem is non-linear also, we forcefully make them linearize it. Why we make it linearize? One problem is that it is simple to handle it. Second thing is that we are able to find out the mean, mode, this all sort of statistics, we can derive it from that with the Gaussian theory actually. There is no theories there which actually handle this non-Gaussian thing exactly. That is why for that this Monte Carlo based simulations or sampling based methods are there which can actually better describe this non-linear or the non-Gaussian part of the data analysis system. So for the underdetermined problems, we have the less data, but we need to answer these things are more. So in that case, there is no straightforward way. So we have to provide some amount of the constant in your problems so that we can constrain the solution. We call it is some damped type of inversion problem, but the constant type of inversion solutions which are able to, which will be helpful to constrain the solutions. So underdetermined problems, we have that, say, two things. One is that you see that so there are two parts, this part and this part. So here you will see this, the first part is related to your complexity related to the models, or the second part is actually related to that, the complexity in the data and the model fitting. And the whole complexity, if you see, of the cost function, that we can define that our algorithm should be like that, it can address both the things. And lambda is a regularization parameters or some Lagrange multiplier that actually handle that. It is a weighting. That when we are giving the weightage, we are paying attention to more in the first part or the second part. So if you see this, the complexity of the misfit functions. Misfit means it is a data model's misfit. That misfit can be expressed by the two types of complexity. One is that your model can be very smooth one, or model can be very complex. Second part is that your data may be very noisy or data may be very accurate. So if your data may not be very noisy, then second part will be your less problematic to handle it. So that is why there is a two things is there. If you want to understand this cost function handling, then you can divide it that whole complexity can be in the two part. One is related to the models, model complexity, model parameter, another is the data. Data complexity is governed by the type of the noise presence in the data. Because you know the theory is perfect, then also we do not have the control about the statistical pattern of the noise. So that is why it may dominate it. But if you see this, there is a complete perfect theory, there is a no noise in the data, then this part you can handle better way. But again, this rest of the part, the complexity can be described by the first part, that whether your models is very simple or the complex. That is also based on the your assumptions, because from the data we have to first use that what type of models are there, what type of complexity is there, then only forward theory can be described it. So that all giving to that part of your underdetermined and the overdetermined part of your inverse problem. And that is why in order to address between that regularization theory has been used. The regularization constants actually give you the two part. One is that this regularization part, if you take it is high, then we are paying more things in towards this one, right side, otherwise the left one. So this is keeping the trade-off between that what type of complexity you are actually addressing in your inverse problem to your optimization problem. So it is a very simple diagrams. We are able to understand that if your observations and the number of the model parameters are the same to be estimated, then we call it event determined problems or the exact determined problems. This type of functions is the Z provides your depth and T is your temperature. It is a geothermal temperature distribution you want to predict from the surface at the any depth. So there we need to have that. Suppose you have a records of the borehole here. This is a borehole. Across the temperature has been measured it at the different depth, and you have a temperature records, and from the temperature records we need to find out that the trend of the curve. So the trend of the curves will give you that the geothermal gradient, let us say, because temperature is varying with the say depth. If these model parameters and the data are the same, then we will use this type of problems, which is exact determined problems, where we are able to find out this model parameter given the data. And this second case is your overdetermined. So here you will see this is a straight line. So straight line will give you y equal to say mx plus c equation. So here m and the c, the two model parameters, but you have your more number of the data which will be used to find out the m and the c. But the thing is that we have to solve the least square based methods, because we cannot fit the straight line each of this point, because it is a straight line. That means you are making a compromise that the slope is best describes the all the data which is considered in your inverse problem. So it is your overdetermined problem. Most likely it has been used, where m estimation is G transpose G whole to the power minus 1 G transpose D. Here D is your data, G is the kernel matrix transpose, G is the kernel matrix which contains the physics as well as the survey type informations of the designs. So this part has to be estimated. Then we have the G transpose. So when we say this whole part is a generalized inverse operator which is applying on the D vectors, which will lead you to estimate the model parameters say m. this model parameter can be different according to your problems. So if you have a resistivity inverse problems, this model parameter will be your true resistivity and true thickness of the each layers of the subsurface. If it is a seismic, there is a velocity and the depth relations in gravity and so on. So this is underdetermined problem we are talking about. Here the number of the data points is very less, but we need to provide the solutions is more. So that means if you say this is a datum, so the possible solutions of this inverse problem is infinite actually. So we can draw any number of the trends which is passing through the datum. Here the datum is your point which is provided to you. That means you have a data point less, but we need to solve this infinite number of the solutions. That is why other way you can say this underdetermined inverse problems where prediction error can be very zero. Because you see any number of points, any number of lines we can draw it, they are also a one solution. And exactly you can predict it, the data. But that is not the case with the other. The other case is that here a lot of noise is there. It may be there that you have to fit it every data points like that. So this is a regressions problems where you will see this that we need to find out this A and the B where the model parameter. If you have know the X, you can predict this Y. This is your forward problems. But if you have a set of data, say different Y1, Y2, Y3, and given this X1, X2, X3, we need to find out this A, B, then your problems will be your inverse problem. So what is forward problem here? If A and B is given, with the help of different X, we can able to find out the Y. That is your forward problem. Inverse problem here, if you have this different Y with the different X, we need to find out A and the B. So you have a set of vectors say Y, you have another set of vectors say X. From the matrix inversions, we have to find out the set of model parameters A and the B. Here A and the B. So this is a problem with the regressions where we are fitting these predictions with your straight line, and that gives you the best or the least square based estimation. So there are different types of inverse problems are there. There can be nonlinear. It is a function of the G. So we cannot write this nonlinear problem directly. D equal to Gm, and then their slope is there. A is your B and B is your slope. So discrete and continuous, linear and the nonlinear, depending on the relations, what is the data and the model parameters, and that gives you that how this G can be formulated and estimated the model parameters in your given data model relationship. So this is the problems of your linear inverse problems, and this is a comes into the fact that whether it can be linear or the nonlinear, but the variations of this Y with this T is actually quadratic, and there is a formulation of the G through which these quadratic solutions can be solved. So we have the data and the models, which is our vectors, and G can be formulated by using this the least squares based methods. We can able to find out that the model estimations with this expression, say G transpose G whole to the power -1, G transpose and the D, where so D is provided. So here the M has to be estimated by solving the least squares based inversions. So this existence, uniqueness and the stability, these are the questions has to be answered of any inverse problems, because inverse problem has to be existed, then only you can solve it. Uniqueness, that most of our geophysical inverse problems suffer with this non-unique. That means that using this same set of model parameters, we are able to find out, or the combinations of the model parameter, we are able to find out the same set of observation. So that is why observation is fixed. So we have a more number of the solutions. That means many of the cases the solution is non-unique. So uniqueness has to be tested. Stability. Stability is another problem because we have seen this some amount of the noise is there in the data that leads to a huge changes in your model parameter estimation. So this property is called that the stability. If your inverse problems is unstable, that means some amount of the noise presence is that it will significantly change your estimations process in your model parameter estimation. Then we call it is a unstable problem. So there is a forward problems, there is a inverse problems, and this even determines, underdetermines, overdetermined problems. We have first we have to understand based on their informations, and then we deploy the types of the cost functions and the inversions technique to find that what is the model parameters and the model parameters. So we can ask it that whether these two type of data points is enough to find out that model parameters. If it is that, then for your inverse problem it is okay. But if it is not that, then we need to think about that their relationship and the types of the informations we want to estimate it. Now we are talking about that that norms. Okay. So we have talked about this overdetermined, underdetermined problems. So in order to have the more smooth version of your solutions, so there is a approach that the smoothness constants which actually lead you that the better solution. So here you will see this Q is your misfit functions where E transpose E, and there is a weighting matrix or the smoothness operator which can be incorporated in between, and we can solve these equations that the derivative of your equations with the first derivative with respect to the model parameters, which should be equal to the 0 to find out these models. And if we solve these equations, we will get that these model estimations, which is again a combination of your G transpose G whole to the power minus 1, G transpose and W subscript E and D. D is your data vectors. The additional thing is that the WE. W is your weighting factors, which is actually acting that there are more smooth versions of your solutions. So this is a one way we can handle that it is overdetermined problems, and we are using this least square based inversions, and by defining this data model relationship with this Gaussian error and with these weighting factors, we can express these model estimations in terms of your smooth versions. So this is a generalized inversion of your least squares methods, where D is related to your GM, and we can see that if the error is not there, we can express it, and these cost functions we can define it by first derivative and their expressions. We can have this expression that model estimation is G transpose G whole to the power minus 1 G transpose G. So this is how we can find that this full expression of your model parameter estimations given the G. So this is your expression of your generalized inverse operator with this overdetermined problems. And here you will see this, even it is a square matrix because G transpose G is there, but sometimes it has in the rank deficient problems, and rank deficient means we are sometimes not able to find out that we are not able to find out that inversions. So in order to handle these things, there is another approach is called this that beta square or the lambda or the damping term incorporated in your least square based inversions. That will give you the two things. One is that this matrix cannot be a singular one because B is considered is your constant, which and square terms will give you that, and so these things can be evaluated without this without these problems, and we are able to find out that the estimations of the model parameter. And the role of the damping is that these dampings will give you that the stability of these equations, and the selections of your damping, again it is a trivial job. We'll see that there are different type of methods are there in the selection of your damping. One is that you can start with the damping randomly, damping factors, and see this what is the observed versus predicts that it should not be a singular matrix. Number one. Second, also it also helps that the what type of noise is there in your data. So that also it is a link with this noise as well as the speed of the optimizations method. Usually this damping has been chosen in a small way. If you choose the damping factor is large, then in a subsequent iteration it should be reduced it through some equation. Either it is exponentially decay or any type. And see this how your error got, means how this with these iterations, how your loss functions has been decreasing it. In electricals, say you are in electrical resistivity inverse problems, there you will see this, the data model relationship is there, which is expressed in your this form, let us say. It is a linear inverse problem, it is a non-linear inverse problem, but you make it linear through some transformation, let us say. Okay. Then you are finding this iterative way to find that model parameter, say resistivity, true resistivity or true thickness of your each layer or your subset. Then you devise these expressions in terms of your damped least square version, say third one, let us say G transpose G plus beta square I is your identity matrix here to the power minus 1 G. Now you have to select this beta. You will see this without beta means there is a no damping. Then your inversion schemes will actually unstable, means it will heavily dependent upon the initial models you are actually considering. If you see this slight change in your initial guess of your model parameter, say true resistivity of the earth, it will actually give you that the results which is not very stable, not consistent one. So damping, if you apply it, then there will be a constant solutions, means the stability of the solutions will be more. And you will get some confidence, okay, after some 3, 4 or 10 iterations or trials, you will get some results which is more realistic to have that. But without damping, it is a very difficult to, because of this instability in the resistivity inverse problem. So the whole thing is that this G matrix can be decomposed using these combinations of the U, Q and the U matrix. Here 3 matrix is your, they are orthonormal, Q is your diagonal matrix. So this Q contains the eigenvalues equations, and this is actually helped to express that. Say let us say in your resistivity inverse problems where change of the model parameters is your, say G transpose G plus beta square I whole to the power minus 1 G transpose del D. Here del D is your change of the data. Here your change of the data means it is a apparent resistivity change. Here del M is your change of the model parameters, and we have to find out the G transpose G and the beta square. Beta is your damping. So this expression is your damped least square based inversions approach. And this G you actually decompose with the help of composition. So this G can be decomposed, and finally this change of the model parameters we can express it with the help of equations. So L diagonal matrix, and these are the alpha and the beta is your the damping constant, and alpha is the eigenvalues of your G. So change in the data is related to the change of the model parameter.
Neighbor point. Change in the neighboring point.
No, change in the neighboring point. It is the
Time to
it is the data of
Apparent resistivity in your electrical survey, let us say. Electrical survey. In gravity, it is the
change in the data gravity anomaly.
well, calculated and observed.
Yes, calculating the observation.
No, simulated apparent reactivity and actual apparent reactivity.
No, simulated apparent activity, this is a change of the this is error. But here it is not error. It is a change of the data into a pattern. So let us say D is your data, at some time you change the model parameters, you change the subsequent data. So change of the D, you change of the data. Corresponding to the change of the model
parameter. So M you are applying, you got this del D, or it is a prediction. Then you M change the M, again you will get the different D. So the change of the D of the data, change of the model here M. So M1 minus M2, D1 minus D2. Let us. So again we will meet at 3.